Good morning, everyone. We'll begin now. So today I'll introduce category theory and how relevance is possible in this. Okay. So I know that category theory is one. Even though you have studied abstract mathematics, abstract algebra, category theory is the next level of abstraction, where what you do is consider all the mathematical structures that you know and haven't been defined yet also, those mathematical structures also, and then try to study those, okay, by extracting out what it means for something to be a mathematical structure, what it means for uh, some or there be some relation between different mathematical structures of the same type. For example, we have groups, rings, vector spaces, cosets, topological spaces, graphs, and so on. And then in each of these particular cases, you have homomorphisms between these objects. Okay. And we have already seen in a little bit, very briefly, how some of the substructures, some of the other things that you define using elements in the case of these structures, because they are all defined on sets. Some of the definitions that you make using elements can also be made free of elements by using functions instead. Of course, functions themselves are defined in terms of elements, but if you create the definition from the element form, then you can make an abstract definition of these things which don't depend on the internal structure of objects. That is the main thing. So when you say group or ring, for example, you need to know what properties they satisfy in order to make it define. But if you observe something general, okay, abstract out, then you can make this independent, make these definitions free of that particular structure, okay, and give some generality. So that is already what you do when you study abstract algebra in the first place. So any of these things, if you take, for example, if you take group theory, they did not start by defining group as an abstract mathematical object. First, how did group theory originate? Yeah, quintics. The solvability of the quintics was a problem, and the related problem was whether you can, for example, trisect an angle or ruler and compass constructions also. Okay. So these problems are related. And then Galois and others, Lagrange and others, had some very unique approach where they said that, okay, instead of looking at the polynomials and just trying to solve them by factorizing or finding factorization, let us look at what happens to these polynomials when you apply some symmetries on them, okay, when you apply some permutations on the roots and so on. Okay, so this led to the study of permutation groups, which was later abstracted. And now what we know as groups, when we study groups for the first time, we start with those group axioms. And then later prove that, oh yes, the group was a permutation group, K is the group. But actually it started out as permutation. Similarly, if you see ring theory, the abstract definition of rings came later. Right. Initially you studied polynomial rings. And of course, the rings of integers and fields of real numbers and complex numbers, these are also familiar. But main thing in ring theory was the study of polynomial rings. Again, it started with polynomials, but then the abstract definition of ring came in. Okay. And so, in all these fields, in all these areas, you have the case where something concrete is defined first, then you abstract it and study it in the abstract. So, why do that? Why do the abstraction at all? Because if you don't do it, many people will be doing the same thing over and over again in many special cases. Correct. So if you study polynomial rings without defining ring in general, just polynomials, and then you prove lots of theorems about them. So you define something similar to ideal. You may not call it ideal. You call it something similar to ideal, and you prove things about it. Another person is studying matrices. Okay, and binary matrices. That also forms a ring. Maybe non-commutative. In that case, also they define something like ideals or two-sided ideals. Then they prove these things. There will be the same thing what the other person proved. Okay, maybe this is because of non-commutation. Then one person just studying integers, number theory on the set of integers. They will also have to do these things. So you abstract the definition of ring, then you can actually put things in the general setting whenever it is possible. And then look at the special case. So special case also you have results that cannot be transferred to other cases. But then you can realize that yeah, this case does not apply in that case because of these particular restrictions. Okay. So category theory arises from the same where you look at mathematics as a whole and say that what are we doing in mathematics, in higher mathematics? We are defining structures, mathematical, different mathematical structures, and then studying different relations between them, okay, or mappings between structures. So how can we do this itself in a more general setting? That is category. Let's start with the more concrete case though. Not exactly concrete case, actually a special version of category theory. Okay. So pre-ordered categories. Again, if you read the part on analysis, then this should be somewhat familiar to you. If you know possets, then this should be familiar to you. Anyway, we'll go through the basics. Sorry. The pre-order relation on a set P is a reflexive transitive relation. That means what? Every x is related to itself, and if x is related to y, and y is related to z, then x is related to z. Okay, this is reflexivity in first angle, transitivity in second angle. So if you have a reflexive and transitive relation, it is a pre-order relation. That's all. No other symmetry or anti-symmetry. In addition, if it is symmetric, then it's equivalence relation, right? And if it's anti-symmetric, then it's a partial order relation. Okay. So it is possible that for two distinct elements also, x is related to y and y is related to x in a pre-order. If we don't have that anti-symmetry. So in that case, if it happens that x is related to y and y is related to x, then x is said to be equivalent to y. Okay. And we write that as this. You can also say x is isomorphic to y or x is equivalent to y. Later on in category theory, this will be when we go to general categories, this will be isomorphism rather than equivalence. But it's a kind of equivalence relation. So in fact, we'll not do this now, but you can, if you're very unfamiliar with this, you can take this as an exercise and write. Okay, because it's a good basic exercise. If you're completely unfamiliar with pre-orders and partial order. To prove that this is indeed an equivalence relation. Okay. So it will be reflexive, transitive, and symmetric. Okay. This one will be symmetric, not antisymmetric. Every element is of course related to itself, right? Because of reflexive. So yeah, two equivalence. Any quick examples of pre-orders? So a set together with the pre-order relation on it is called a pre-ordered set. I will just call it a pre-order. Okay. Some people call the relation pre-order. I will call the set under the relation pre-order. If you call the relation pre-order, then the set has to be called something. I mean, this structure has to be called something else. So some people call it pro set. Some people call it pre-set because but that has a different meaning, more well-known meaning. So we won't call it. Fine. Any natural examples?
Integers under divides.
Integers under divides relation. So if you take integers under divides relation, this is the pre-order, but it's not a partial order because 1 divides minus 1 and 1 is 1 also divides 1. So in fact, 1 is equal to minus 1. Okay, in this notation. Yeah, any other example? So here the only any element can only be equivalent to at most one more element, right? Any non-zero element will be equivalent to one other element. Other than itself, one other element, right? 0 is of course only equivalent to itself. 0, everything divides 0. Nothing 0 does not divide anything else other than 0. Okay. Yeah. Any other?
Power set of X is subset.
Okay, power set of, if you take any set X, okay, then the power set of X under the subset relation. This forms a pre-order, but in fact it forms a partial order because subset relation is anti-symmetric. A subset of B and B subset of A, then A is equal to B. So the equivalence relation in that case becomes equality. Okay, if you take a what is called a partial order. So I think I defined that later. So I just mentioned partial order to come back to pre-order. So partial order relation is a anti-symmetric pre-order relation. Okay, if whenever x is equivalent to y, it turns out that x is equal to y. That means distinct elements cannot be equivalent in that pre-order. In that case, we call it a partial order. In order to call it a partial order. So then you call it this structure then is called a partially ordered set or coset. Again, that also sometimes people call that itself partial order set also. Yeah. So example of partial order you already told me. So for example, if you remove those negatives from the set of integers and then consider divides relation, because the only problem to antisymmetry there was element and negative are equivalent to each other, right? So if you remove those, then you get a partial order. This is the partial order. Okay. Even this natural numbers, because you don't need any existence of any special element for making partial order. So you can remove whatever you want, it will still be a partial order. Any subset of this also will form partial order integers. And as I said, you take any set X, its power set under the subset relation is a partial order. In fact, again, you can take any collection of subsets of the set under subset relation. That is also a partial order. You need not take all the subsets, any collection, any sub collection. That is also a partial order. So any good example of a partial pre-order which is not a partial order. This is one example. Okay. But here you have just small equivalence classes. In logic, can you think of anything in logic? Okay. Suppose you have a set of all propositions in some formal system. Okay, like in piano arithmetic or whatever, you have some set of propositions. Proposition means what? Statements. That means things with true or false value. And anything with a true, for which you can assign or for which there is an assigned true or false value. That's called a proposition or statement. Okay. So you have the set of propositions under something this forms a pre-order. Under a particular connective or relation between propositions. That would be an operation. You want a relation. Conjunction is and, I think. Implication. So if you take the set of all propositions in a particular formal system and take the implication relation, P implies Q. P implies itself. If P is true, what does P implies Q means? If P is true, then Q is true. We just say if P then Q. Right. Meaning if P is true, then Q is true. Okay. So if P is true, then P is true. Yes. So it is reflexive. If P is true, if P implies true and Q implies R, then P implies R. Right. So it is transitive. Is it anti-symmetric? One statement implies another, and that statement implies this. Does that mean it's the same statement? No, they are equivalent statements. That's why we say no, when proving theorems, something very familiar to anyone who does mathematics. Because when proving theorems, many theorems are characterization theorems are what? The following are equivalent. Characterization theorem means the following are equivalent. That means first one implies second, second one implies first, or second one implies third, third implies second, and so on. All of them imply each other, means they are all equivalent, right? They are all equivalent. So if P implies Q and Q implies P, then we write P implies Q, right? Or wait, P if and only that this in that particular case becomes the if and only if relation equivalence, right? But the statements are literally not the same. an integer is odd. If and only if it is not even. Right? Like that. Because you know more of it. Okay, then from a pre-order, we can always get a partial order by quotient. That means, so I'll also show you the hazard diagrams for pre-orders. There's this direct approximation. So, so this is, for example, a hazard diagram for pre-order. Actually, this is just the graph of the pre-order. You can clean it up a little bit by eliminating some redundancies. Yeah, that is actually sufficient. As a hazard diagram, this is more properly a hazard diagram. Well, there are different ways of drawing. It's not exactly a unique way like in partial order. Because, for example, these two elements are equal. So I could also have drawn the arrow here instead of this one. Okay. They're more or less the same. Okay, so you are able to read this diagram correctly, right? So maybe if I name this element C, B, this means A and B are related to each other. A is less than or equal to B, B is less than or equal to A. So that means A and B are actually equivalent under our equivalence theory. It's not partial order, it's real order. Okay. A and B are both related to C. A or B less than or equal to C. C is less than or equal to D. C is less than or equal to D. E. D and E are not related to each other at all. So they are incomparable elements. That's why we call it partial order. Okay, in this case, pre-order. But why in this also? Why is it partial? Because there may be elements which are not related to each other in either direction. So they are incomparable elements. That's why it's partial, not total. If you have a partial order in which every element is related to every other element in one way or the other. Okay, one way or the other only. So partial order. And it's called a total order of change. Okay. So this is an hazard diagram. Now I want to make a partial order out of this. So what I'll do is I'll take the equivalence classes. So this is the equivalence class of A as well as B. This is the equivalence class of C, just C itself. This is the equivalence class of B. This is the equivalence class of E. Okay, they are all singleton because they don't have any other things equivalent to that. And then corresponding to those, so I call this class of A, class of C, class of B, class of B. Now observe that A is related to C. Of course, also to D because C is related to D. Also D because C is related to D. Right? But B is also related to C. Okay. So it doesn't matter which representative I take here. That's what you asked to prove here. Okay. So it doesn't matter which representative to take. Even if I wrote B here, then B is also related to C. Why? Because B and A are related. So B is related to A. So if A is related to C, then B is related to C as well. Right? Similarly, if B is related to C, A is related to C as well. So that is well defined. That this, so I define this relation as given here. Right? Class X less than or equal to class Y, if and only if X is less than or equal to Y. So it doesn't matter which representative of the class you take, it will be well defined. Again, I give it to you to verify if you are not convinced with this. We will not spend more time on this. Just verify it. So this is the quotient pre-order. This is the quotient partial order of the pre-order. Quotiented by, you can quotient with any equivalence relation. I mean, not any, but several equivalence relations. But this is quotiented by this particular equivalence relation that is naturally defined. Okay. So when you quotient a pre-order by that equivalence relation naturally defined on it, you always get a partial order. So in fact, when you are studying pre-orders, very often it's enough to study the partial order associated portion because you are more interested in the relations between those non-equivalent elements rather than between equivalent elements. Equivalent elements anyway are equal. There's nothing much more that you can say about it. Okay, moving on. So any pre-order, I will call it also a pre-order category. Okay, nothing much different here when I call it pre-order category, except that I think of it as a graph rather than as a directed graph. So like my earlier example. So slightly modified. So these are I draw double-sided arrows rather than drawing two arrows. These are equivalent. These are equivalent. And let's say this is related to this, and this. So, for example, here. Okay. So really, there are some arrows here which are not mentioned. So this is the Hasse diagram. Then when I consider it as a pre-order category, I have to also consider all these arrows. Because they exist. So clear how those extra arrows come in? I may have this one or two maybe. Right? Yeah. No, that's good. Yeah. Yes. Nothing much. In Hasse diagram, you can leave out some of the arrows which are deducible from transitive. So this green arrow was not there earlier, right? Point. So this arrow was not there earlier because I can deduce it because there is an arrow from this to this and this to this. So I know that that relation must be there due to transitivity. So that's all. So in fact, here also actually there was something more written. This also is not needed. Okay. Yeah. But here I will add. That arrow also is redundant because two elements are equivalent. A is equivalent to B, B is equivalent to C, then A is also equivalent to C. So yeah. But when I think of it as a pre-order, when I call it a pre-order category, I will think of it as consisting of an object consisting of these vertices and edges or arrows. Okay, so I'm considering it as being made up of two things. One is a set of vertices, which is that P itself. Okay, and another is the set of arrows of P. Okay, which are completely defined by the pre-order relation. That's it. Okay, but I'm thinking of the arrows as elements of a set. Okay, because earlier what we had was a relation. You can think of it as a relation that is actually what is the relation? When you say R is a relation from A to B, what does it really mean? R is a subset of A cross. So actually that's what this is all about. You are going back to thinking of it as because that only this pre-order relation that you have. When you think of it as a subset of P cross P, that's just what a set of ordered pairs. Okay, of elements of P, indicating which elements relate to which. So that's it. So I'm just considering now thinking of it as arrows. This just to see it as a graph. Okay, but later when we go to general categories, there will be something more general here. I mean, I'm forced to think of arrows for something. Okay, I'll come to that. Yeah, because in the relation we say that A is related to B means mathematically it means AB belongs to the set R. We write this is just notation that we introduce. Correct. Similarly, for function we introduce the notation A is equal to F. But again, that means A comma B belongs to the relation F. Okay, that means F for the set. The function is also a subset of A cross because of relation in some condition. Correct. So everything is ultimately a set. But we don't keep thinking of it as sets. We think of it as rules for assignment or relation and first. Okay, so here, yeah, this when you consider this AB now as an arrow, then you can consider it as a component of the pre-order as a category. Okay. The pre-order category. Okay. Don't worry about it too much. When we go to general category, you'll see why. Special cases which I'll maybe use once or twice. A pre-order category or pre-order is discrete if no two distinct elements of P are related. What is a discrete topology? All the sets are all the subsets and all the subsets, and then there is a power set is a topology on that, right? So it is like all the sets are isolated, right? I mean, all the points are isolated, correct? So here similarly, discrete category means you just have elements are related to themselves, but nothing else. Okay, so this is a discrete category. In the graph incline. Whereas a co-discrete category means every two elements are related to each other. That means it's a complete relation. Okay, this is not quite the empty relation because empty relation nothing is related to anything. Here it's like the smallest possible pre-order relation. You start with an empty relation and try to add the minimum possible things to make it a pre-order. What is the minimum you have to add? You need reflexivity. So you make everything equivalent to related to itself, and that's it. Stop there. Don't add anything. Right. Whereas here, this co-discrete means everything is related to everything else. Okay, in both directions. Both directions, that's important. In partial order, you can't do this. In partial order, you can't have relation in two ways. So partial order, the best you can have is a total order, which is change. Sorry?
Why don't we put no here?
Oh yeah, it's there. Yeah, again. In fact, here also it is there. Right? I forgot to add it. In fact, there are loops because usually we treat it as understood. I forgot. That's right. Actually, there are loops also. So in every not as a diagram, when you consider it as category, you have to add the cell loops also. Okay. Fine. So co-discrete category means everything is related to each other. That means this we think of it as this is equal to P cross P, the complete relation, the full. Okay. Fine. So what will yeah, I already answered. Fine. Okay, what can you say about the graph or what I mean by this question? What will a partial order category look like? Yes, as a graph, what can you say about it? Loops are there, but I mean, Hasse diagram, yes, you won't have loops because by definition, in Hasse diagram, you don't add the loops; they're implicit. But as a graph, what can you say about it? Yes, that is a pre-order category, correct? In a pre-order categories graph, what you will have are every strongly connected component, graph. Every strongly connected component will be sorry, I went back to this question because he speaks not discrete. Discrete, not discrete. So first question is, if you take a pre-order category, it's not mentioned here, I'm just asking you now. If you take a pre-order category and the graph of that, what if anything can you say about the graph? What is a strongly connected component of a graph? It is a maximal subgraph in which every two vertices have a path from each to the other. Okay. So in a pre-order categories graph, that means a pre-order category considered as a graph, every strongly connected component will be, that's what you said earlier. Will be a click. Will be a click. Okay. Because the existence of path. See, for example, as a graph, okay, fine. As a graph, this is strongly connected. You can find a path from every vertex to the other, but it's not a click. It is not complete. However, when you if it is a pre-order, then this also has to be there. This also has to be there, and this also has to be there, right? So it will form a. That's already there. Yeah. So all of these vertices will have to be adjacent to each other in the graph theoretic term. That will form a plane. So every strongly connected component will be a plane. Okay, I don't want to go into graph theory. Plane means a complete circle, maximum complete circle. Maximum complete circle. Yeah. So every strongly connected component will form a plane. That's right. No. General. In general, for a pre-order category. No, it's only strongly connected component will form. Okay, let me make this here. So you take so here, this is a strongly connected component. There is a path from every vertex to all the other vertices in that, and that's a maximal subgraph in that problem. This is a strongly connected component as well. Okay, but together they are not strongly connected. If you consider them together, or even if you consider one vertex from this one and this one together, they are that won't form a strongly connected subgraph because there is no path from this one back to this. Okay, there is a path this way, but not the other way. So that property is not. Similarly, this alone is a strongly connected component. I am not drawing the loops again, but they're there. I am not drawing the loops. So each strongly connected component has to be clicked because of which property? Those are little, but like what is the property that poses you in a general graph, in a general directed graph, this is not true. You can have strongly connected components which are not clicked. Which property? Transitivity. Whenever you have a path from A to B, there will be an edge from A to B. Such in graph theory also such directed graphs are called transitive graphs. In an undirected graph, you don't consider it because it is useless. Because it's always you will get just complete graphs. Okay, so in a directed graph, this thing is called transitive graph. If the property is there that whenever there is a path from A to B, there is an edge from A to B. Such a graph is called transitive graph. So in transitive graph, we strongly connected component will form a thing. Okay. Yes. Now the question again. What will the graph of partial order category be? Not necessarily a path. That will be a total. Wait. Yes. So okay. What will be the strongly connected components then? Only singletons. Strongly connected components have to be singletons because as you can see, they are equivalent. No? So because of anticipatory, no two distinct vertices can be connected to each other in that, right, in both directions. So that is one thing. And therefore, you can have the simpler form of Hasse diagram where you can drop the directions from the diagram, right, or partial order instead of drawing it this way. In draw diagrams, the Hasse diagram, like this, without any arrow. By showing the direction of the relation by moving upwards. Yeah, paths can only be there in single. If you take one vertex to another, there can only be a path in one direction at most. Right. So, I mean, this is also, there need not be paths. So, you can consider it a single poset. So, this is very well the poset. Okay. So, yeah. This is a coset. So you can have paths and at most one direction. In this, you are seeing it as undirected path, but actually you can only go in the upward direction. Take that as a rule. So the arrows are implicitly there. Loops are implicitly there. Arrows are implicitly there in this direction. When you go from this vertex to this vertex, yes, that is an arrow. When instead you go from this vertex to this vertex, no, there is no such arrow. It just the upward direction indicates the arrow. And you can draw this consistently. So this case won't occur here. This case occurs, then you cannot indicate direction by arrow. Because there may be two elements which are related to each other. Then which direction, what will you draw up? Right? And you can't escape that by drawing all of them on the same level also. That will also lead to some problem. Okay, so again, moving on, but very quickly, to review what I said. So pre-order is the reflexive transitive binary relation on set. So think of pre-orders as graph sets, where some things are related to something else, whatever. And whenever you have this is related to this and this internal related to this, and these also are related. That is transitive. Everything is related to itself. That is reflexive. So pre-order in which no two distinct elements can be related to each other in both directions. That is partial of the. Fine. Then you have the opposite or dual of pre-order. So you have one pre-order p comma less than or equal to 2. You define another relation on the same set by saying x is greater than or equal to y if y is less than or equal to x. You can verify that this is also a pre-order. Okay, if p comma less than or equal to 2 is a pre-order, then so is p comma greater than or equal to 2. That's also a pre-order. That pre-order is called the dual of the first one. So sometimes we say consider the pre-order P by different, like we say consider group G, although it's actually G comma some operation. That's okay. But in this context, we already have to mention the relation because, or else you have to say P is actually the something like their set, and this is the pre-order, and then you have to use this notation of saying it is this. That's also okay. So then P is the tuple itself. Okay, the structure is. So yeah, if P is a pre-order, then P of is its dual or opposite pre-order. And then observe easily that the opposite of the opposite is itself. Okay. So what this leads to is the principle of duality. Any statement that you can make or any theorem that you have involving a pre-order leads to another theorem, okay, about pre-orders, where if you replace this by this relation. So if you have a statement that is true for all pre-orders, then you get another true statement for all pre-orders by replacing this relation by this relation. Or in other words, whenever you have in your statement, in your theorem, whenever you have some part which says x less than or equal to y, then you can replace it by y less than or equal to x throughout. Okay, throughout your statement, everywhere in your statement, consistently. Then you will get another theorem. Okay, nothing remarkable because both of these are pre-orders. But this has to be something that is true for all pre-orders, only then. If you take a particular pre-order and you have a particular statement true in that, then taking the dual of that statement in this way will not give you another statement which is true in the same pre-order. It will be true in the other pre-order. For example, here I can say that here it is true that there are two elements such that well, actually there are three elements x such that a is less than or equal to x. If I try to make the dual statement and say that okay, so then there are also three elements x such that x is less than or equal to a. No, that is not true in this pre-order. It is true in the dual pre-order. Of course, the relation won't be denoted that way. It's true in the dual. But if you have a statement in general, right? suppose, for example, okay, when we define join union, then we can mention, then we'll come to it. So I'll come back to duality later. Example. So now again, when you have two different pre-orders, or maybe a pre-order and itself, how do you relate? Again, you know you have group homomorphisms, vector space, linear transformation, and so on. Yes?
But in that, we have
What?
other dimension.
No, this will be true in the dual pre-order. Not in the sense, that's the point. This will be true in the dual pre-order. That's my point. You can only dualize statements that are universally true, means true in all pre-orders, not in one particular. Okay. So a monotone map from a pre-order P to a pre-order Q. Specifically, pre-order P with this relation less than or equal to P and less than or equal to Q is the other one. Because you have to be careful with this. Is basically a function that preserves the order. Preserves the order means, so here you have x is related to y. Then after applying the function, this is in the first pre-order. And the other pre-order, maybe this depends. Okay. Maybe send x to this x, and this y. What must be true is f of x must be still less than or equal to 5. I mean f of y. Okay. Then it's called, if it's true for all xy, then it's called monotone. Okay. And if it consistently reverses the direction, so I'm sorry, this is the type. Okay, this is the type. It should be less than or equal. I'm sorry, please correct. Other one is still a monotone. Actually, this p comma. Yeah, here it is correct. Okay, but actually, if we take this to the definition, then you can prove this is an x. And the type. Should be q comma, same pre-order q. Only p is replaced by its dual. So monotone map from the dual of p to q to just q. That is called a antitone map from p to q. P original p to original. It's okay if you don't introduce the terminology also, because we can always talk about monotone maps, and whenever you want, you can take the dual. Fine. But again, it's an established terminology, especially in category theory, we'll see the corresponding analogs of this. Fine. Okay, let me give a quick example. Quick example, considering what we did earlier. Suppose you have a set of propositions in some formal system, and you map them to, so I'll introduce this, actually, forms, I'll figure it out. And introduce that pre-order. So again, what I'm leaving out is what is implied by reflexivity. True is related to itself, false is related to itself. In addition, so the only additional things I'm saying is the pre-order. In fact, a partial order. False is related to true. Okay. You have false is related to true. This is a pre-order. Now here you have a set of propositions, but let's say the set of all propositions to something. You map each proposition to its truth value. Is this a monotone or antitone? Whatever. What is it? So what does it mean? Suppose you have proposition A implies proposition A implies a proposition B. Then is it true that f of A in this f of A will be less than or equal to f of A means the mapping to the truth value. So is it true that f of A will be less than or equal to f of B or other way or any, nothing can be said? What? Why? Okay, let's see. It's just because it's just two values you can consider basically two tables. Yes.
Or it's nice to
Oh, you can. False implies true is a true proposition.
always.
Yeah. Or actually, the definition of this is if this is considered to be true. If and in fact, I will tell you that this is tautologically equivalent to what? Using actually this implication is a connective we introduced later, but this can be expressed in terms of and or and. Not P or no, not P or not P or right. It's equivalent not, which means either P is false or Q is true. Why? You bit of a digression, but okay. I'll quickly discuss this. Suppose someone tells you that if you study this particular question, you will definitely pass the exam. When can you say that the statement was false? They are not saying that if you don't study, you will fail. If you study this particular question, you will definitely pass the exam. That is what they told you. When will you say that they lied? If you studied it and then you didn't pass the exam, right? Yeah. You studied it and you still didn't pass the exam. So that means the only way for that statement to have been false is P is true, but Q is false. That is okay. Because I did not say that if you don't study, you will fail. I only say if you study, you are guaranteed to pass. That's all. Yes? If you studied and still failed, right? If you studied and still failed, then you say, okay, that was a lie. That was a wrong statement. If you studied it and passed, yes, fine. If you didn't study it and failed, fine. If you didn't study it and passed, still also fine. Right? Because I'm not saying if and only. If you don't study this, you will fail. That I didn't say. Right? So, yeah. Okay, so then again, think about this. Suppose you have A implies B. Now, let's just consider the different possibilities for A. Suppose A is true, then B should be true. Correct. That means, yeah, f of A is less than or equal to f of B. In that case, if A and B are both true, then it is true. F of A is less than or equal to. Suppose A is false. B may be true or false. Doesn't matter. Whatever it is, F of A is less than or equal to. Because false is the least value. So this will be a monotone loop. Right? In fact, this may be not the set of all true, this may not be the set of all propositions of something. It could be, yeah, proposition is something you assign the truth value. So suppose you have a belief system, you believe a set of things about whatever, about something. It is consistent if this map is monotone. Your set of beliefs, you may not have thought about all of them in relation to all the others. You may believe this thing and the other thing, and some third thing, and some fourth thing. When you actually connect them, it may turn out to be consistent. Inconsistent. Okay. So it is consistent only if this map is monotone. the mapping of truth, the beliefs to their truth values. That turns out to be monotone. Then your belief system is consistent. Okay, moving on. Right. So if you have a function from a discrete preorder to any preorder, it is monotone because just to remind you what discrete preorder was. From a discrete preorder to any preorder, any map is monotone. Why is it? Discrete means no two distinct elements are related. So you can map anything to anything, and there is nothing to satisfy because this condition, right? What is it? Yeah. In fact, that's another example of P implies Q into Q. This will always be false except for x equal. For distinct xy, this will be false. Oh, right. There's another type. Sorry. Sorry, I was too sleepy when I was typing it. So, yeah. So, whenever x is not related to y, f doesn't have to satisfy any condition for x and y. Right? That's another thing. That's another example of what we discussed just now. When the condition is not true, then you don't say that the other thing has to be false. Right? It's like if x is not related to y, then you don't say that f of x should not be related to y. That is not the definition of monotone. So let's take another example. Okay. So discrete preorder, any monotone, any function is monotone. And similarly, if you take function from anything to a co-discrete, the codomain is co-discrete, then in co-discrete preorder, everything is related to everything else. So again, it doesn't matter what you're mapping from or how you're mapping them. Ultimately, everything is related to everything. So this, again, the condition is backwards satisfied because if Q is true, then P implies Q is always true. The same thing. This coincidentally turned out to be right. This is the question. What are the monotone maps from a co-discrete preorder to any partial order? What can you say about this? That means map should be, map is called, such a map is called, the image is singleton. That means constant. Okay, so the only monotone maps from a co-discrete preorder to a partial order are constant. If you generalize this to preorder, then you can say they are the images contained in one equivalence class. If you make the codomain preorder, the domain is co-discrete, you can say they are maps such that the image is contained inside one equivalence class of the domain. Okay, let's move on. We can try these examples later also. Yeah, just a second. I'll order the tea for the break. Hello, advanced department. 11 o'clock. More 20%. Maths department maybe. Please now the yeah, first. Okay, so as usual, we can define isomorphisms between preorders. So preorder isomorphism between preorders is a bijective monotone map, but on additional condition, which you don't see in the case of algebraic structures like groups and rings. What is that? The inverse also has to be monotone. That won't automatically follow. In groups, when you define isomorphism, you say that it's a bijective homomorphism. That means f should be bijective, and f of xy should be f by x f of y. You don't also say that additionally f inverse of say u v must be equal to f inverse u times f inverse v. right? That will automatically follow. Here, it won't automatically follow that the inverse is monotone. Inverse may not be. For example, again, you consider bijection from a discrete pre-order to a co-discrete pre-order of the same cardinal. Okay. So here, everything is related to everything else. So I'm not drawing all the arrows, but just understand that everything is related to everything else. In the discrete pre-order, only elements are only related to themselves, nothing else. This you consider bijection. Any bijection. This is monotone, correct? And it's bijective. But is the inverse a monotone match? Impossible. So this is not automatically an isomorph. Okay? This is not an isomorph. You have to separately check whether the inverse is also a monotone. Okay. That's another example like this in a different area of mathematics where you have to put the condition of the inverse. What is that? Homeomorphism. When you define homeomorphism, it's a continuous bijection whose inverse is also continuous. They are unique in system. Yeah, so it's important to saying this. That's all this. Yeah, I think you don't need examples of all of these things. So we'll move. Now, take me to the next slide. This previous Excel. This one? Oh, yes.
It's not delivery. Yes, that's what. How can we?
If and only.
What is the second condition says? How we can tell that it is a
It is a bijection already. Given that it's a bijection. So here you have xy. Here you have f of x, f of y. This is a mapping, suppose. Now, you're okay. Definitely it's monotone, correct? This implies it's monotone. You are saying the inverse may not be monotone. Okay. So if I say that x is not related to y, then is the condition satisfied? Is that condition satisfied? Only if of x less than or equal, right? So no.
in the definition, then the inverse condition is not required.
No, in monotone you have if and only if it's not. It's only one direction. In monotone, simply the definition of monotone is that x related to y implies f of x, not if and only. Simply implies. Yes.
Reorder isomorph. We to by taking more of the completely. This one is inverse condition is not required.
No, that's the example again. So to take simply this pre-order. It's a pre-order because everything is related to itself, nothing else. This is another pre-order. I'm considering a map. Understood. Okay. This is monotone and it is bijective, but its inverse is not monotone because this thing is missing. Okay. Yes. Yeah, fine. So now, suppose you have two pre-orders P and Q and different maps between them, monotone maps. Monotone maps between them. Okay. Now I want to say that I'll use this notation. I'll make it clear why later. It's not implies something else. Okay. I want to say that f is less than or equal to g in some sense. So I will define this as F is less than or equal to, in fact, less than or equal to G. Here I'm using this arrow, but I'll write F is less than or equal to G. If and only F of X, yeah, pointwise comparison. Okay. So I'll give a quick example. You take R under the usual order, Z under the usual order. Consider two maps. So floor, ceiling. Consider the floor and ceiling maps. Floor means what? Every element is rounded. Every real number is rounded down. Okay. So from 3.5 or 3.1 also becomes 3. 3 becomes 3. 3 remains 3. 3.1 becomes 3. 3.9 also becomes 3. Whatever you take, so floor will round it down. Okay. Doesn't matter whether it's 3.5 or more or less. That doesn't matter. Whereas ceiling of 3.9 will be 4. Okay. Ceiling of 3.9 will be 4. Is one of them less than or equal to the other in this order? Floor of X is always less than or equal to ceiling of X. Correct. Floor of X is always less than or equal to ceiling of X. Correct. So this is it. Now, therefore, let this bracket, square bracket P comma Q denote the set of all monotone maps from P to Q. This is this bracket PQ. It's not interval. It's just I'm not using intervals here, so I'm using this notation for this. So it's a set of all monotone maps from P to Q. That forms a pre-order under this comparison. Because you can do that, this is also a pre-order relation. Is that more or less obvious why this is a pre-order relation? Because it's pointwise. So usually pointwise maps, when you define operations or relations pointwise in the function, that whatever that object satisfies, usually the maps, the set of maps also will satisfy. Just because it's pointwise. Sorry. So yeah. So this one's a pre-order. Okay. Okay. Some other concept only. Now upper set. Now upper set in a pre-order. So again, I will mostly take partial order as examples because pre-orders are too messy to draw and don't add much value. So I'll draw partial order. I'll draw the arrows also, it's not required, just to make it clear. If you're seeing partial orders for the first time, then you will not be used to reading maths at diagram. So I'll keep the arrows there. But I will avoid the loops. You know that everything is straight. Okay. So consider this. An upper set in a partial order P is a set such that whenever you have for any x in that set, anything below it is also in that set. Okay. Read the definition carefully. An upper set of a pre-order or partial order P is a set, it's a subset of P, such that whatever element you take in that, everything below it in that order is also in that set. Okay. So, for example, This is an upper set. Sorry. This is an upper. For example, you take this element. The anything below it itself is always there, but that's nothing to check. This is there. Yes. You take this element. What elements are going to? This one, it's there. This is there. This is there. Similarly, if you take this, whatever is below it, you already have checked. Right. In fact, it's enough to check the somewhat largest element. So, this if you take whatever is below it, is there. Correct. What about this element? It's not there in the set at all. So no condition to be satisfied. Okay. This is called an upper set. Lower set is similarly defined, where you just take the dual. So when you have duality, all the definitions also have duality. Whatever definition you make has a corresponding dual definition. Some of the definitions may be self-dual, they won't give you anything. But this is definitely giving you a new, they call it lower set, but I have not defined it here. Yes, sir.
Last point.
Sorry? No, I'm just showing you that if an element is not in that set, then it doesn't have to satisfy any condition.
For it's belongs to the
The three. Oh yes. I think I gave it a lower set. I inverted it, sorry. You have byte system. All right, this is obviously the lower set. I'm sorry. Upper set is what? I'm just giving the lower set, not upper set. Sorry. So, yeah, it is upper set means it is closed under the operation of going up. Okay, that's it. It's closed under, sorry about inverting that. Closed under the operation of going up. So, for example, I can take this is an upper set. Fine. So, upper set means whatever element you take, everything above it must be there. Yeah, it is closed under going up. That's why it's called upper set. Fine. So, when you take this, there is nothing above it other than itself. So, it's okay. Trivially, that satisfies the condition. When you take this again, trivially, it satisfies the condition. But now, when you take this one, what elements are above it? There are two elements above. So yes, this is there and this is there. Again, these will trivially satisfy the condition because there is nothing above them, nothing else above them. Okay. Similarly, this one will satisfy because again, this one, this and this. Okay. Whatever is above should be in the set. Is it clear? Anyone wants me to explain the alpha set? Huh?
yes, related. Belongs to P. It's going on with the why related.
Divided on three.
Let me read it. Upper set is a three for all x in P.
If there exists a y set that y is given for x, then y belongs to you. Lower sets. Upper set is similarly for all x in P. Suppose there is a y set that y is greater than x.
No,
If
correct.
you take one
If there exists y in U, such that y is less than U. Yeah, this is correct. Oh, but I think I explained it wrong. This is correct. The definition is correct. I explained it incorrectly. Yes, what was it?
let's suppose you take the bottommost x.
Yeah.
There exists y in U such that y is greater than equal to x for upper set. You have an element of
No, the definition is correct. My explanation was not quite correct. Okay. So, yeah, I got it wrong. Once again. It is not merely closed, it is definitely closed under going up. But that's not it.
It's
No, that's good. Yeah, anything about anything, please.
for the definition, if you take X to be the bottommost matrix there, and
Okay.
if you take Y to be, say, the rightmost bottom one,
Yes.
there exists Y in U such that Y is less than equal.
No, no. Why is it? You are saying take. So sorry about not naming these things, but if you call this A, okay. Now what are you seeing for A and B?
No, not for A.
Oh.
Start with B.
Okay.
You can use that for X in the definition.
Okay. V is equal to you take this as X. Okay, but what Y will you take that is below X?
Go to vertices up into the set.
But there is nothing less than or equal to Y. See, for this to for you to check the condition say it's not working, you have to find the Y inside the set, which is less than or equal to X. So is there any Y other than X, which is less than or equal to X? That's all. My explanation was it messed up, I think. You need, if you have any element inside the supposed upper set, which is less than or equal to some element X, then X should also be inside. Okay, so I think that is correct. When you take, so the thing to check is, you take every element inside the upper set, simply confirm that everything above it is inside. Okay, please. Yeah. Yes, the entire set will be upper and lower set at the same time. That is correct. Yeah, that's the same thing. Yes. So only thing I think additional condition is there that will have to be sublattice also. Since here we have not defined join and weak yet, so that is not. Yes, they will have to be closed under join or weak as well. They have to be sublattice with which is simultaneously upper and lower set. Yeah, the upper set is you can define in the partial order.
Set will be upper.
No, because okay. So you take, suppose you try to claim that this is an upper set. Now, can you find if you take this? Now, if you take this as X, is it true that there is some Y inside the set which is less than or equal to X? Yes. Is X in the set? No. Therefore, this is not an upper set. Okay. So, very simple way to think. The definition is written slightly awkward way, but the simple way to think about it is closed under what operation? Operation of going. We are not defined that as an operation or anything. That's why we are not doing. Okay, but it's closed under the operation of going. Okay. Yes. If you have a singleton which is not related to anything else, that's what you mean. That will be upper or lower. Yeah. Because there is nothing above or below it. If you have a singleton which is not connected to anything else, then that will be simultaneously an upper and a lower. Okay. Singleton which is not related to anything. I mean, a point which is not related to anything else, that means it's okay. So this exercise that I think we will do. Define first of all this U of P. U of P denotes the set of all upper sets in B. Okay, we'll do it through an example. Okay, and I'll take a partial order. Okay, I think that's general enough probably to take care of corner cases also. To be upper case. Okay, we consider few of them. not all the upper sets, a few of the upper sets. So, for example, the entire set, it's like maybe a label. So, the entire set P is an upper set. Then E and F singletons are upper sets. So, if you take such elements, then they will also form singleton upper sets, but not singleton lower sets. These are also upper sets. Suppose you take an upper set containing C. What is the smallest upper set you can take which contains C?
C.
CEA. ECA. Smallest upper set containing D.
Yeah.
DH. Then of course you can take CD, EF. Okay. And then smallest upper set containing B, BCDEF. Okay. And then P is already there. That is smallest upper set containing A is P itself. I guess that's. No, there are a few more, right? At least one more. DEF. Is there an upper set? It's closed under going up. Yeah, maybe that's the only other one. I think we got out of them anyway. We don't, it's okay. Now, this is the power set of P. The power set of P naturally forms whatever set you take, forms a partial order under subset relation. Nothing, we are not using this structure at all, just subset relation. Okay. So under the subset relation, power set forms a partial order. So do the inclusion mapping from this set. This is probably, let's say only something, it is 2 of P. Now when you take power set of P, how many will you get? 2 power 6, 64 subsets will be there. Okay. So we are not going to list all of them, but define I as the inclusion mapping from this set, which are some subsets of P, to the power set, which are all the subsets of P. Is this a monotone map? Right. Is it a monotone map? That's the question.
The decision holds.
Okay. Yeah, both are subset only. Yes. So it's a monotone map. Fine. Yeah, that's correct. That's what it means. It's a monotone. Fine. Okay. Okay, then let me see. So you think about this problem. Similar to the earlier category B, it's just a relabeled version of that. This I is just a category, the pre-order category. In fact, partial order category 0, 1, with 0 less than or equal to 1. That's it. Okay, if you think of it as false and true, just 0, 1. Okay. To consider any pre-order, P comma less than or equal to. This is the thing. Now I believe that the monotone maps from P to this particular special category are in one-to-one correspondence with the other sets of P. Do you know a similar result in set theory? And in topology first. Similar result in set theory. So basically, how many elements are there in the power set? What is the cardinality of a power set of finite set? Set object. Yes, sir. Finite or infinite? If A is a set, what is the cardinality of the power set? 2 power n. means to power cardinality. Why? Value is the indicator or characteristic function of subsets. That means your subset X of A with the characteristic or indicator function of X is 1 if X is in A is in X, 0 if A is not in X from for. Okay. So this is a function from A to what's it? It's a function from A to 0, 1. Right. This is in set theory. And in fact, suppose you consider this was a set 0, 1. And what does this notation mean? Set of all functions from A to 2. A to the set 2. Whose cardinality is this? Okay. Because the subset, so the subsets of A are in one-to-one correspondence with functions from A to this thing. Okay, so there is a one-to-one correspondence between subsets of just a set, not pre-ordered. Just a set A to this particular set. Similarly, in topology also. Suppose you take a set A, define the topology of it. Stop. Probability set. It's B and this also I call it. It's not correct. Okay, I'll just call it T. T. Then you take any topological space X. The continuous maps from X to this T are in one-to-one correspondence with open subsets of X. Okay, continuous maps from X to T, X to this particular topological space, are in one-to-one correspondence with open subsets of X. Okay. This that you can verify later, all those things. We now come to this particular case. We have some pre-order. Again, we can consider partial order for simplicity because nothing much changes. And have this special pre-order. Check all the interval. It's not a general interval, it's just something called interval. Interval pre-order. Just one particular one. Take any monotone map from this pre-order to this. That will give you a unique upper set. And vice versa, you take any upper set in this, that will give you a unique monotone map from this to this. The question is how to do it. Yeah, now we break for T, think about this table to break. So we'll continue now. Okay, so we're trying to solve this problem. It says that the upper sets of a pre-order are in one-to-one correspondence with monotone maps from that pre-order to the particular pre-order, interval pre-order 0, 1. Okay, 0 less than or equal to 1. Why is it true? Without writing the formal proof, let me try to give simple argument. Take any element which maps to true under this map. Suppose one particular element maps to true. Okay. So I call it green. What else must definitely map to true if it's a monotone map? Anything about it. So if you take that, that is an upper set. Okay. And the others, the map, those map to red, and those map to say that those map to false, color than red. And the green colored points form an upper set. Conversely, suppose I give you an upper set, then can you give me a naturally defined monotone map from this? Yes. Map all the elements of the upper set to true, all the elements not in that set to false. That will give you monotone. These two constructions are inverse to each other. Means given a monotone map, I can get a particular subset which happens to be upper set, which is a pre-image of true. That is, that's it basically. If you take, if you take an element here in the set of all monotone, the pre-order of all. Okay, that comes later. If you take an arbitrary monotone map from P to I, say F, map it to F inverse of this F inverse of 1. Here I use the notation 0, 1, correct? Yeah. Not false and true. You think of 1 inverse. So if you take F inverse 1, this is what some subset of P. But what subset? It's an upper set. Okay. So this definitely belongs to set of all upper sets of. And if I give you an upper set, so if I take an upper set here, with a mu, then define a function. Basically, what function is it? That characteristic function. Map it to the characteristic function of u as a subset of p. The characteristic function will map all the elements of u to 1 and all the elements not in u to 0. That is a monotone map. Because if anything maps to 1, anything else is above it, that will also map to 1 because it's the upper set. So it's a monotone map. And these constructions are inverse to each other. I mean, these maps are inverse to each other. Correct. Is that right? So I start with an upper set with the characteristic function, and then apply this. Take the inverse image of that. What will I get? U itself. And vice versa. Okay, you will verify this later, but without writing it formally, this is this convinces. You just consider a monotone map, it will look like this. Means it will naturally partition the set into two parts. It's the upper set and not the complement of it. The upper set will be by definition all the elements are mapped to one. Okay. That's it. So there is no unknown correspondence. But it's not just a bijection. We know already that this is a pre-order. This set of all monotone maps from any pre-order to another pre-order forms a that functions set. That set forms a pre-order under the point-wise comparison relation. So in fact, this is a percent isomorphism. Is it? I'm claiming that this mapping in here is actually a percent isomorphism. I mean pre-order isomorphism. It's an isomorphism from this pre-order to U of P. U of P we already noted here. Yeah. U of P is a subset of, it's not really a pre-order, it's a subset of the set of all, I mean the percent of all subsets, the power set. Power set as a subset. Okay, back to lattice, but yeah, power set, percent, it's a subset of that. It is a subset under the inclusion relation. So that's what I'm saying. Here, this is set of all upper sets under the inclusion relation. The relation here is inclusion. Whereas here, you have monotone maps and the relation is this one. F is less than or equal to G. If I leave point-wise, that is true inside the pre-order P. We say that F is less than or equal to G in this interval, not interval, in this set of monotone maps from P to the interval. Okay, I'll leave it to you to verify. We move on. Because I have to go to actual categories also, not just pre-order. But that's an important thing. Right? Yeah, you take okay, the induced mapping. So you take a monotone map from the pre-order P to pre-order Q. That induces a mapping from, in fact, that induces a mapping from U of Q to U of P, opposite direction. That induces the mapping F star from U of Q to U of P. So you have some monotone mapping from P to Q. We define F star from set of all upper sets of Q to set of all upper sets of P. Okay. As just F star is nothing but pre-image map. Sorry? You're not able to what? But we need to be already. We need to be already. 48.
Different people that has
Yeah, you're looking. Yeah. Some. Okay. Yeah. So. So first thing is it true? I mean, what kind of mapping is it? F star to U, Q to U of P. What can you say about this mapping F star? F star is just pre-image. Okay. Yeah. Yeah, correct. For all you, yeah, it's not really correct. Universal dependent element. Yeah, I should have made it clear. For all you mean capital Q. Correct. That's okay. For all you mean the set of opposites. Correct. So for just so if you take U in this, map it to the pre-image. So firstly, is it a well-defined mapping means what is needed for well-defined this here? It's not a problem of representation. This F inverse U should be an upper set. Is that good? Or do you quickly see that it's an upper set? Use the previous exercise. You know characterization of upper sets in terms of functions. An upper set is equivalent to means once you have this isomorphism, you think of an upper set as merely being a function from P to I or Q to I, whichever upper set you want. Take an upper set is basically is essentially a function, a monotone function from P to I. Okay, because the one-to-one correspondence is there, right? That is the thing. So, if you take an upper set of Q, that's equivalent to what? A monotone function from Q to I. A monotone function from Q to I. Now, what does it mean to take pre-image of that? Because you have a monotone function from B to Q. This is P to Q. Okay. This upper set defines a particular monotone function from Q to I. And if you have that function, so if I call this some L corresponding to the Q, if I have the characterization or correspondence between function upper sets and functions, what exactly is U in terms of MU? How did we define it here? It is just the pre-image of 1. Alright. This upper set U is just, if this is the mapping monotone mapping line, this is just pre-image of 1. This U is pre-image of 1. So here, this is MU. Then this upper set is actually pre-image of 1. And now F star of this is what? Pre-image of that set. So ultimately, what are we getting? Pre-image of this mapping. For some mapping. Okay. It's in fact the pre-image of this composition applied to 1. Because you have two monotone maps. And the composition of monotone maps has to be monotone. It's easy to see. So this is guaranteed to be what? An upper set. Because the pre-image of a monotone map from that interval. Whatever pre-image of 1 of that interval of a monotone map. Whatever monotone map you take from P to I, you take the pre-image of 1, you get an upper set. That is the previous characterization. So this is definitely an upper set. That's all. So definitely F star is a well-defined mapping from upper sets of Q to upper sets of P. Okay. And yeah, this phi T and phi Q are the canonical isomorphisms which map these things. So yeah, this is that one. Basically, I will show that. Okay, anyway, I have sent you the PDF already. It's shared on the group. Try this exercise later. Otherwise we won't have time. We'll move on. But this is an important exercise. We'll do it in somewhat more detail. Now I'm going to define some special upper sets. You can think of it as principal upper sets generated by one element. So this is, you take an element X in a pre-order P and take all the elements about it. That is definitely an upper set. Arbitrary upper sets are not of this form. They are not principal. If you call this principal according to usual ideal terminology, arbitrary upper sets are not principal because we may have some components. Right? But this is specifically definitely an upper set. So I'm taking the upper set of X. Okay. Upper set of X is defined by a particular element X, one element X, single element, set of all Y. Such that X is less than or equal to Y. That means set of all Y above X. Okay. In a pre-order form. It could be. Anyway, you can think of partial orders, simpler. So this is easy to verify. Definitely going to be an upper set. Easy to verify. You don't do it now. Consider this. Because it's an upper set, you can consider it as a function from P itself. Right? P is a pre-order. U of P is a pre-order under substitution. So now this arrow, the upper set, is a function from P to U of P. Correct. Because given any element X, correspondingly you get upper set generated by the X. Upper set of X or upper set generated by the X. So it is a mapping from P to this. Is it a monotone mapping? That means suppose X is less than or equal to Y. Can I then say that upper set generated by X is contained in upper set generated by Y? Is it? Oh yeah, P of sorry, yeah, right. Oh yes, then upper set generated by Y is containing upper set generated by Y is containing upper set X. Why? Because X is less than yeah. It's inclusion reversal in the sense that they are ordered. But why is it true? That's correct. This is antitone. So, if X is less than or equal to Y, then Y itself belongs to upper set generated by X, and therefore anything above Y must also be. Simple reason is if X is below Y, anything above Y is also above X. So the upper set generated by Y, consisting of all the elements above Y, is contained in upper set generated by X. Means elements, these are not elements above Y. Okay, all elements above Y. These are all elements above X. But you have X itself is below Y. So anything above Y must be also above X. Simple thing. That's it. Okay. Yeah, but this mapping reverses order. Right. Yeah, so it's an antitone map from this given pre-order to its corresponding pre-order of upper set. Now, is this true? It's a stronger claim. The one way you already have. This implication is already there. It's a converse true though. We are not saying this is a bijection. I mean, actually, here we have not proved that it's a bijection, but is it? It's not a bijection between this and all the upper sets. It's a bijection between this and the image. It's an injection. All upper sets are not necessarily principal unless the pre-order is special. Y belongs to? You are going in the reverse direction, correct? Yeah, so if upper set of Y is contained in upper set of X, then y itself is, oh, that's what you said. Y is always there in upper set of y. Y is there in its own upper set. So now it is there in upper set of x. Okay. This is just another way of saying. Y is in the upper set of x means y is above x. This is another way of saying x is related to y. So this is a special case of the resultant category theory called unit dilemma, or specifically unit embed. So what if you be your view of what's happening here? You have an arbitrary pre-order, which is somewhat abstract. Because just a set of some elements, I don't know what those elements are, but I can define whatever relation I want between them. Or verify that it's a pre-order. Like if it satisfies those properties, it's a pre-order. So this is abstract in that sense. Like the pre-orders are defined by axioms, right? Those axioms of what a pre-order relation is. But this is what is something concrete. Concrete means the relation here is not some abstract relation. It is particularly a subset relation. Okay. So what, for example, in case theorem, what we do? We take the abstract group where you don't know what the elements mean. They are just labels. Then the operations also, they are just defined like that. They don't mean anything. Okay. But you then convert it to some subgroup of symmetric group. But you know what the elements of symmetric group are and you know what the operations. Elements of symmetric group are bijective functions, that is permutations from some set with them. And the operation there is function proposition. So you are taking abstract group and making it concrete. Here similarly we are taking an abstract pre-order and making it concrete in the sense that it is a sub-poset or sub-pre-order of the, in fact it's a sub-partial. Right? Only thing is, yeah, there is some subtlety, I'll talk about it. So suppose this is a partial order, P is a partial order, then this will be an actually injective function. This will be actually injection. It's a partial order. Otherwise, there is some loss of information, which is that two different elements may go to the same upper set. Right? Suppose x1 and x2 are equivalent elements in the pre-order. Then they will both go to the same upper set. That way the information is lost. But still, if you have a partial order, then you are getting a concrete other thing. And the fact is that usually, if you are only interested in elements up to equivalence, then this loss doesn't matter. Okay, so we'll quickly define join in place. So if you have a data like this, suppose you have two elements x and y in a pre-order p comma plus 1 into an element z. It's a join of x and y. Element z is said to be join of x and y, written as join y, c y. If first of all both x and y are related to it. So z is above both x and y. Above meaning related to, like x and y are related. And for anything else, any other w to which x and y are related, that will also be automatically related. Okay. If you can find any other, so you think of z as an upper bound. Just think of it as upper bound. So z is an upper bound of both x and y. Firstly, if you have any other upper bound of x and y, then z is less than or equal to it. Okay. So it is in that sense least upper bound. That is the supreme, right? That is called the join. So you can generalize this to any set. You take any subset of P and then do the same thing. So you want a common upper bound of all the elements in the set, such that if you have any other upper bound of the same set, then this particular upper bound will be related to that. Right. So that is called the join of that set. Okay. That set could be infinite also. Your pre-order is infinite. That set could be infinite also. So in general, join may not exist. If it exists, we call it join. But when you're considering pre-order rather than partial order, there is another problem here when they write like this, there is some problem with that. What is it? Is this a well-defined operation on a pre-order? Even if it exists, even if it exists. Huh? It may not be eating. In a pre-order, you can have two different. So, for example, so A is an upper bound. In fact, A is a join of X and Y. Because X and Y are, okay, let's say something else added. It's not really needed, but anyway, let me just add. Okay, the transitivity implies X is related to this thing and we call it 1. X is related to 1 and Y is related to 1, all that is there. But observe that A is a join of X and Y because A is the upper bound of both X and Y. And if you find anything, including A or 1, that X and Y are both and B also, then A is less than or equal to that. Correct. Here, B is also one possible upper bound of X and Y. But A is less than or equal to B. So it is satisfied. Correct. But B also satisfies the same definition. Correct? Because B is an upper bound of X and Y. Now, if you take any other upper bound of X and Y, that is A or 1 or B itself, B is less than or equal to that also. B is also a join. So this is not quite well defined. But again, the point is this is unique up to equivalence. They have to be equivalent because of this condition. If you find two different upper bounds of the same set, then in two different joins of the same set, this is join X and this is also the join X. Okay. Then by this being joined, it has to be related to this. But because this is joined, this has to be related to this. So they will always turn out to be equal. So up to equivalence, it is well defined. Okay. So this is up to equivalence well defined. In a partial order, you don't have to worry about this because anti-symmetry ensures that there is a unique one if it exists. Okay. Now, what is a meet can be similarly defined. What is the meet of A and B here? This example, meet of A and B. Is X a meet of A and B? X a meet of A and B? A and B are joins of X and Y. And this is not. One, it is A and B are joins of X and Y. Is X a meet of A and B? So it is true that X is a lower bound of A and B. Is it greater than or equal to every lower bound? No, Y is also a lower bound of X and Y. I mean, Y is also a lower bound of A and B. But X is not related to Y. Y is not related to X. So neither of them is a greatest lower bound or meet. Okay. So A and B do not have a meet in this example. X and Y have two different meets in this example. Okay. A and B have a join. Unique one. That is one. Similarly, if you take if you are not included as an exercise problem. Oh yeah, here it is. So firstly, what are X join X and X meet X? X itself. Okay. Suppose X is less than or equal to Y in a partial order. Then what are X join Y and X meet Y? Y and X respectively. So X join Y will be Y and X meet Y will be. So the picture will be X is below. In general, you should have this picture. These are special cases where the diagram is not going to look like this. In general, join and meet look like that. This other picture. Okay, let me leave out something there. Join in, join is unique up to equivalence that already discussed. Yeah, meet is defined here and meet is similarly. In a power set, in the coset given by a power set of some set, what are join and meet? Union and intersection. Join is union, right? Above. Intersection is meet. Intersection. Here are other examples. Again, that road theory notes also some examples. Again, skip partition. You can try those things later. I'll skip partitions. That's just mainly I'm using it as an example for or counter example for. So suppose you have a monotone map from P to Q. It is not necessary that it will preserve joins and meets. Okay. I want to give you a quick example. Okay, I can give a particular example, concrete, not concrete. Okay. Absolutely. It's a monotone map. Yes, but we can label the things. A is only less than or equal to A and C. Okay. With A, you don't have to. A is less than or equal to C. Image of A is 1. Image of C is 2. 1 is less than or equal to 2. So, okay. B is only less than or equal to other than itself C. Image of B is 0. Image of C is 2. 0 less than or equal to 2. So, okay. A and B are not related, but that's okay. This I'm not saying this is isomorphism. It's merely a monotone. Happens to be bisective, but anyway, that also I don't need. But does it preserve joins? Does it preserve joins? For example, what is join of A and B? C. What is join of 0 and 1? 1, not images. Okay. So join of A and B is C, which is close to 2. But join of 0 and 1 is 1, which not 2. This is a mapping, like you can concept more natural examples. So that partition thing would have given you some natural examples, but it's too much to explain for this example. Okay, so we won't go into. So definitely, it is not necessary that monotone maps preserve joins and mix. That's why when we define lattices are partial orders in which every pair of elements, not every arbitrary subset, every pair of elements has a join, every pair of elements has a meet. Huh? So in that case, a monotone map is not necessarily a lattice homomorphism because it may not preserve join and whereas in lattice you have the algebraic structure join and means join and inner operations. So this operation that will be preserved if you call it a lattice homomorphic. Monotone maps are poset homomorphisms, but not necessarily lattice homomorphisms in general. Even if the poset happens to be lattice. So that's why. Join and meet don't necessarily get preserved in the monotone maps. But this much is true. Suppose you have a monotone map from P to Q, and those are two partial orders or pre-orders. Think partial orders for simplicity. And suppose a join of x and y exists. Then definitely f of x join of f of y exists, and it is less than or equal to f of x join y. Equality you can't exist. But this is okay. Okay. So I think we won't do it. But can you, as an exercise, tell me the next statement? And then do it later. Okay. If X meet Y exists, then f of x meet y is less than or equal to f of x meet f of y, which must exist. Okay. So if you prove the first one, how do you prove the second one? Just say by duality. That's an example of duality. If you prove the first thing, this is true for all posets. All posets P. So then, if you replace, obviously you must have noticed the join and meet are just dual to each other. If you replace all less than or equal to with the definition of join by greater than or equal to, you get the definition of meet or vice versa. Right. So here, if you replace join by meet, you get this. But correspondingly here, what do you do? This join gets replaced by meet. This join gets replaced by meet, but this less than or equal to gets replaced by gives you one which is greater than or equal to, which immediately gives you the next statement. So once you prove one, by duality you get the other. So all these theorems in this theory come in pairs, except for the case where it's some equality that you prove. Or meet. Some statements are self-true, some statements will not give you anything new. They said that trivial statements. Even if it's equality here, right? Suppose somehow you prove that they're equal, then also you get a new statement because for meets. Only thing is, if it's join on one side, meet on the other, or something like that, then it might happen that you don't get any new statement. Those are not very common. Okay, so this is the main thing here. The Galois connection, also called adjunction. But adjunction we use in the terms of case of categories. So here specifically it's called Galois connection. So take a turn to understand this. The Galois connection between two pre-orders is a pair of maps in opposite directions. One F from P to Q, corresponding G from Q to P. Satisfying those relations. That is, for all small t belonging to P, not for all Q belonging to Q. F of P is less than or equal to Q when only P is less than or equal to G of Q. The map is changed. F of P is less than or equal to Q if and only if P is less than or equal to G of Q. Some strange definition, but we'll see examples of this. Keep occurring repeatedly in different areas of mathematics. That's why it's named like that. If you studied Galois theory, you already know this. Maybe not in that start form, but you definitely know examples of this. If you study Galois theory, that's where the name comes from. Galois theory of, Galois fields and groups. That is something strong on Galois correspondence. Galois correspondence is it will give you bijection, F and G. Here F and G are just maps, not necessarily bijections, monotone maps. Okay. So you have these monotone maps. So in this case, you say that if this happens, then F is a left adjoint of G and G is a right adjoint of it. Or you just say that F is a left adjoint, meaning that it has a right. So if I just take a monotone map and without reference to any other map, if I say it is a left adjoint, that means there exists some G in the opposite direction. For instance, like we say invertible means there exists some inverse. Unit means some inverse exists. Like that. So it is a left adjoint means there is right. But this definition is not symmetric. Means left and right do matter. Okay. This G you cannot. So when you define inverse of A, you define inverse of A as like A into B equal to B into A. It's equal to identity element. That's a semantic definition. A also happens to be inverse of B. But if you define something like right inverse of B in some algebraic structure with the operation, you define A is a left inverse. Suppose you say A is a left inverse. If it has a right inverse, that means this will be equal to whatever is the identity. So then that definition is not symmetric. A is left inverse means it is left inverse only. You can't conclude that it's a right inverse. B is a right inverse. Okay. So similarly here, in fact, this is something very much like left inverse and right inverse. Okay, when you don't have proper inverse, this is the next best thing. Okay, so let's go to maybe an example here itself. Consider these three maps. The inclusion map from the set of integers, not just set, whole set of integers. Okay. So integers form a poset under less than or equal, not divides. Under less than or equal to, Z forms a poset. In fact, total order A is less than or equal to B, usually, in usual sense. Similarly, R also forms a poset. Now consider the inclusion map from I to R. Is it a monochrome map? Yeah, because basically identity kind of function, only the domain is larger, right? Codomain is larger. But basically everything is mapped to itself, the orders preserved. We already saw that floor and ceiling functions are monochrome maps from R to Z. Okay. Now, take, let's say, take P here. Maybe to make it more familiar to them. So n is an integer, x is a real number. So suppose f of n is less than or equal to x. That means what? F of n means here I of n. So only one map in that direction. I of n is less than or equal to x. Means what? I of n is what? N itself considered as a real number. Okay. So that means n is less than or equal to x. Okay. Can I say that ceiling of n is less than or equal to x? No, sorry. Can I say that, okay, I'll first ask this thing. Can I say that n is less than or equal to lower of x? Is that true? Think carefully. Not necessarily. Yeah, it is true. Yeah, n is less than or equal to floor of x, right? Because n is an integer less than or equal to x. Floor of x is the greatest integer less than or equal to x. So yeah, that would be easy. Okay. Yes. N is less than or equal to x. It's the converse to the. Suppose n is less than or equal to floor of x. Then is n less than or equal to x also true. So this is defined only. So what does it mean? The inclusion map is left. Okay. Keep forgetting that inclusion of marks here left hand. Yes. Inclusion map from Z to R is left adjoint to floor. Okay. Maybe we'll visualize this. Okay. Okay, obviously I can't depict all the real numbers, but we don't want all of them. Maybe some in between. Okay. What it says is, if I take for it, inclusion map. Looks like this. The other map that is floor. Floor looks like what? 2 maps to 2, but anything below 2 will map to 1. Right. Okay. So inclusion map is left adjoint to floor map. That will look like this. Now let's look at the other one. Suppose x is less than or equal to n in the set of real numbers. In R, x is some real number, n is an integer. Okay, in real numbers, x is less than or equal to n. Actually, I should say, suppose no, rather, suppose this is ceiling of x. Ceiling of x less than or equal to n. Yeah. So this happens in Z. X is a real number, but this happens in Z. Correct. Ceiling of x less than or equal to n. Can I say that x is less than or equal to I of n? Ceiling of x is least integer greater than or equal to x. So that means n is definitely greater than or equal to x. Right. If n is greater than ceiling of x itself, n is greater than or equal to x also. You can just take a simple example. If I try to make it very large, 2.999, ceiling of that, I can say it's less than or equal to 3 or 4. That means x itself is less than or equal to 3 or 4. Correct. I cannot take 3.1 here and then take 3 on the other side. So definitely this is true. What about the converse? This is true. What about the converse? Also true. So in fact, the ceiling, this shows that yes, ceiling map is left adjoint to inclusion map. That's one thing why they are not actually inverses of each other. Because ceiling is left adjoint to inclusion, is left adjoint to floor. Floor and ceiling are not the same. Okay. This kind of thing here. In fact, you can have more. You can have a larger J. Here won't happen, but you can have a larger. I think here also you can get probably, but you can have left adjoint, right adjoint, and so on. Because they're not the same. So that would look. Okay, you know what the diagram data. That looks something like this. Fine, let's go. So we will not prove this, but I just wanted to get the definition. So if I have a function from x to y, can I get a function from opposite of x to opposite of y? Hey, going to F, okay, just map every subset to the image of that under that function. Okay. So f star of A is equal to f of A mean of all of A. That is definitely a subset of y. So that mapping. What about in the reverse direction? Can I get f upper star from power set of y to power set of x? Inverse image. So that is take all x in x, such that f of x belongs to B. That gives me the reverse direction. Now X and Y are not pre-orders of integer. P of X and P of Y are pre-orders. So now you have two maps. One is F lower star from P of X to P of Y. And another is F upper star from P of Y to P of X. Okay. Right? You can verify maybe later that this gives you a Galois connection or a junction. Think about it. But this is something that you already almost know or definitely know. We discussed before also, maybe not completely. Remember, SL of G is a subgroup lattice. So this is an extended version of the correspondence theorem. Correspondence theorem tells you what? For groups. That if you take N is a normal subgroup of G, then subgroups of G containing N are in one-to-one correspondence with subgroups of G mod N. Okay. This is correspondence theorem, and then it tells you some other things like normal subgroups will correspond to normal subgroups, and so on. Anyway, that is correspondence theorem. This is a slightly extended version where even if you take something which is not containing it, suppose you take some subgroup, it's not necessarily containing N, but still you can have this Hn. This is obvious from the correspondence, you don't need to separately put it. Hn will be the join of Hn, right? The smallest subgroup containing both H and N. And that will have the corresponding, right? What will that be? Hn model. So Hn model is not just H. I mean, it is not H model because Hn is larger than H in this case. If H does not contain N, then Hn will be larger than H. So Hn model will correspond to that. Okay. So you can still have a mapping from the entire subgroup lattice. This. Of course, both of these are two distinct subgroups. H and Hn are two distinct subgroups, both going to H. It's not a bijection. Whereas normal correspondence theorem gives you bijection. That's a Galois correspondence. This is a Galois connection. That's it. Because it's not a bijection. Okay. So everything here will go to something over there. And vice versa. You take any subgroup here, you can come back in the usual way. Any K model if you take, that corresponds to some subgroup K that contains it. Okay. So in fact, the idea here is closure. That is when you compose and you match the data on one data or closure. So in this case, this extension is defined with respect to the particular normal subgroup N. So what you get is if you take G is coming back, right? So if you take G of f of x, what does it give you? It gives you Hn. So it is in some sense closure. Okay, closure operator. Closure operator, what are the properties of closure operator when you generally define? They are idempotent operators. And monotone. They are idempotent monotone operators. So that is the composition of what else? Also, yes, correct. They are extensive, right? So this will be definitely greater than all. Okay, actually, I think that is the next exercise. I think showing them without naming them. So in any Galois connection, if you take the composition in one side, on one side it will be closure operator. On the other side also it will be closure operator on the dual. Okay, because it's just they're this dual sub each other. Like left head joint, right head joint will become reversed if you dual take the dual. Okay, so they're both closure operators in some sense. One on the other, one on the dual. This is like you take closure in the with respect to N, meaning you take the smallest subgroup containing it. I mean containing that and then. That. Right. So this is that. This is asking you to show that one of them is this is extensive, because this will be greater than or equal, less than or equal. Yeah, correct. This is extensive. So the composition G, the right adjoint applied after left adjoint, that will be greater than or equal to IDP in the pre-order that we define. We concretely what this means is that for all P will be less than or equal to G of f of P. And here for all Q in Q, f of G of Q will be less than or equal to Q. Okay. So this is a characterization of an adjunction or Galois connection. F and G in those correct directions are form a Galois connection if and only if this is true. If and only if those compositions are particular kinds of closure operators. So some intuition behind this is that the adjunction is like the closest thing you can have to inverse, but there are different kinds of approximations. F and G are different kinds of approximations. So when you go and come back, you get something like the best approximation in some sense. In one direction it will be lower, in the other direction it will be higher. That is the thing. Yeah, think of again seeding and this one. So if you go from real numbers to integers and come back, right? Two ways of doing that. You can go as using seeding, then come back. That will always give you an integer greater than or equal to whatever you started from. Whereas if you go to Z using floor and then come back, you will get an integer less than or equal to what you started from. Okay. Yeah, I think we'll skip this and go to general category. But this is again a special case of what you can prove in general categories. Okay. So we saw in general that joins and means are not necessarily preserved by monotone maps. But if you have adjunctions, then yes, in the sense that left adjoints will preserve joins, right adjoints will preserve means. That is true. Okay. Left adjoint need not preserve meet. Okay, and vice versa. So left adjoint will definitely preserve join. So quick check here. Sealing is a left adjoint. Correct. Join operation here is what? In a chain, what is join operation? Max. Join of two elements in integers or real numbers, whatever under usual ordering is, the larger of the two integers. So when you take sealing, that is preserved. When you take floor, mean is preserved, right? So just think of it. And in fact, this characterizes adjunctions in a special case. So not in arbitrary preorders, but in preorders where all joins exist. We have seen that joins may not always exist. But suppose you have a preorder, which you do in many natural examples. You have preorders where joins exist. Okay, so it will be semi-lattice, at least in partial order also. You can call partial order, you can call it. It will be either mean semi-lattice or join semi-lattice or complete, not complete. Fully a lattice in many cases. So in that case, you can apply this. An adjunction will be exactly something that, so left adjoint will be exactly something that preserves joins, and right adjoint will be exactly something that preserves means. Monotone map that preserves. Monotonicity you can have separately check to preserve. So again, we won't do this. Yeah, we'll stop in 15 minutes, but I'll introduce this so you can have some idea. And then we'll continue for a little while afterwards. So, don't worry, let's start with So this is just a summary of all most of the things which we cover up to natural transformations. So actually, that's what categories, then functor, natural transformation. If you just list the definitions, it's only this much. Definition of categories, definition of function, definition of astronauts. It's only this much, but we need to do some work to understand that. So think of familiar categories, sets and functions. That's a category. Groups and group homomorphisms. That's a category. Vector spaces over given field and linear transformation between them. That's a category. Rings and ring homomorphism. That's a category. So on. Okay. Posets and poset homomorphism, monotone maps. That's a category. Okay. Not one pre-order as a category which we saw. Different, all the posets or pre-orders you take and monotone maps between them. That's a category. So what is the abstract version of all of these? You have some collection of objects like sets or groups or rings or posets. Then you have a set of morphisms, okay, between any two given objects. So maybe empty circles, but so if you take two objects x and y, then you have, in the familiar case, you have homomorphisms of different kinds between them. Like this function for this, linear transformations of vector spaces, monotone maps for pre-orders or partial orders, true homomorphism for groups and so on. But in general, just something going in that direction. So again, if you abstract out without trying to define what that is structurally. So like, again, remind you, in a group where we define in the abstract, we don't say that group elements are permutations. We don't say that group operation is composition. It's just a name given. Even if you call it composition, it's just a name. You don't define what it should do, only how they behave with each other. If you compose three things, what should happen in such things? You don't define structurally what a composition does, right? Group composition. Similarly here, X is just a label or just a name. This arrow is also, so if you can name it if you want, but they are just names. You cannot say that F looks like this, G looks like that. The abstract definition. But what you can say is, this is a set of all arrows from X to Y, set or collection of all arrows, not one set. And you have some other Z. Okay. So again, you have some arrows from Y to Z. So remember, in a pre-order category, if you have an arrow from, say, X to Y and an arrow from Y to Z, then you should have an arrow from X to Z because of transitivity. Here also that happens, but here it's something stronger because here you have several arrows from X to Y, possibly. Several arrows possibly from Y to Z. Corresponding to each pair, you must have a pair. Okay. So if you take one F from here and P from here, that must, corresponding to that, there must be an arrow, which we denote P circle F. Think of functions. You have a function from X to Y, Y to Z. You have a composition of those functions from X to Z. So similarly here, there must be a composition. Remember, composition is written in the other order. So P after F from X to Z. But corresponding to F and Q also you must be there. F and R also there must be. Maybe some of them are same. I don't say that they should be different, but there should be one corresponding to G and Q, G and R, G and B, and so on. So all this. So you may get up to, in this case, you may get up to 9 different morphisms. Maybe some of them are same, but you should have all. Okay, they should all be defined. That's it. So just like when you have two elements in a monoid group, the composition must exist in that. Okay, so some other C and some other C and D, when you compose, maybe you get AB equal to CD. That's not a problem, but you must have corresponding to every pair. Here, when you consider all the objects together, all the morphisms together, like F and G and R and all that, you just consider all of them together in one collection. You can't say that composition is a binary operation on that collection. Why? Because, for example, F composition G, in this F composition G, is it defined? No, we don't say that it's defined because you can call X the domain and Y the codomain as usual. So the domain of G is not the codomain of F. Okay, F goes from X to Y. G does not go from Y to something else. It also goes from X to Y. So this is not defined. So this composition is a partial order. Partial operation on the collection of all arrows or morphisms of the category. However, whenever you have this condition that codomain of F is equal to domain of G, then P after F must be defined. That is a rule which you have stated in a more understandable way here, that whenever you have F in form XY, the collection of morphisms from X to Y, and G in form YZ, collection of morphisms from Y to Z, then G composition F must exist as a morphism from X to Z. Okay. Again, think of usual examples. This is nothing new. Only thing is, we don't say that they should be functions or anything. Just axiomatically, they should satisfy these properties. That's secondly, fourth thing is, every element F must have at least one morphism from itself to itself, from it to itself, which is the identity morphism, satisfying some particular property that is given there. The property is it behaves like that. Okay? Called identity because it behaves like the identity. That means what? That's a term. Okay. You have the identity morphism 1x or idx from x to it. It should satisfy the property that if you compose these, okay, this should be equal to f. F composition with 1x, the identity of x, should be equal to f, and similarly, you have one y, and the composition of one y after f should also be equal to f. These are the two properties to be satisfied by the identity morphism for any arbitrary from x, y, and 1x and 1y for the identity morphism. So every object has an identity morphism satisfying this property. Okay, this is just a normal sanity condition that home xy is disjoint from home AB. Okay, the morphisms from x to y cannot be the same as morphisms from A to B if x or A are different or y or B are different. That's again, normally you won't even think that that could happen. So your intuition already tells you this. Yeah, and then you need associativity of composition. Whatever this abstract definition is, that operation, that partial operation, should satisfy associativity whenever these are defined. Whenever this composition is defined, and this composition is defined, and this composition is defined, and this is defined, associativity should be satisfied. Okay. Examples: sets and functions, semigroups and semigroup morphisms, semigroups and monoids and semigroup homomorphisms. That means you know that all monoids are also semigroups, but a semigroup homomorphism is what? Function from say S to T such that f of xy is equal to x f of y. That's all. Monoid homomorphism means what? Identity also preserved. So you can also consider monoids, but with semigroup homomorphism. That will also form a category. Okay, it will form what is called subcategory of the category of semigroups. Okay, but those won't always be monod homomorphism. That will not form a subcategory of monod category. Okay, it will be larger than the monod. Monod category will be internal subset of subcategory of that. Okay. Similarly, topological space and continuous maps are topological space, and homeomorphism is more strongly graphs and homomorphism, rings and unital ring homomorphisms, or you can have this category if you want of possibly non-unital rings and non-unital homomorphisms, and so on. Vector spaces over a particular field. they form a category. Okay, you can take over any field also. Only thing is that won't give you anything new because there will be no morphism from vector space over one field to vector space over another field. So it is as good as studying those categories separately. It's not that they don't form a category, you can do that. Okay, fine. 3 times 40. Okay, I'll show you this example itself for now. Okay. So you call a category small if the collection of objects forms a set. And if you haven't studied proper set theory, then don't need to worry about it. You think of every collection as a set, then it's okay. But you know that leads to some paradox. If you think that any collection of sets or any collection of objects will form a set, you know there are paradoxes possible, right? Russell's paradox. You can define a set of all sets. If you can put anything in set, if you say a set of all sets, and you can define some strange sets which then turn out to be empty. So just to be careful, you have these things. So some things are sets, some collections are sets, some things are proper classes which are not sets. Okay. So don't worry too much about it, just for the sake of complete correctness. So category is small if its objects form a set. So the examples that we saw here, these are all large categories. I think, yeah, these are all large categories because a collection of all sets and functions is itself not a set. It's a proper class. Collection of all semi-groups and morphisms, that is not a set, it's a class, and so on. All of these form classes, but not sets. So what is an example of a small set? One is a small category. One is this. You take a group G. To define a category, you can call it G itself, but for better clarity, we call it BG usually. Okay. So BG is a category which there's only one object. You can't ask what that object is, it just is some object. You don't even need it. But in the group, you have different elements, so A, B, C, D, X. You define them as morphisms here. Again, there is no question of how they are morphisms, you just call them morphisms. You don't have to explain how they work, only how to compose them. Then they have to satisfy the axioms. That's it. Like when you form an abstract group, if I say that, you know that, if I say that EABC is a group and AB is equal to C and so on, you don't ask me why is AB equal to C. I'm defining its term. Similarly, here when you say that I'm calling these morphisms, you can't ask why it is a morphism or what it does. I can only tell you that A composition B will be something, B composition A will be something, and so on. But notice that I have to define composition of every two morphisms here. Why? Because there is a single object. So the domain of anything is equal to codomain of anything because there is only one object available. So I have to define all these morphisms. In the group, I have some operation dot no. So I will simply define this as A. That's it. Now it satisfies these axioms of category. What are the axioms? Associativity of composition. First of all, composition should be defined whenever the domain codomain match, which it does because I am defining it for all pairs of morphisms, including morphism itself. It's well defined. Okay, I mean it's defined. Associativity, is it true? Is this circular operation associative? Yes, because it's basically the group operation which is associative. So that's fine. Existence of identity morphism. For every object in this category, there should exist an identity morphism. How many objects are there in the category? Like one object. So I should have one identity morphism. So consider the identity element E or 1. What do you call it? Is it the identity morphism? Does it satisfy the property? That is, E is the morphism from that object itself. Now, if I have some other morphism, say A, from some object to this, maybe that object only to this. According to my definition, A after B is A dot E in the group. But what is A dot E in the group? A. To satisfy. Like after one B. Yes. It is satisfied. Similarly, if I take B from that object again, only single object available, so I can't do anything. B from that, this composition, what is it? B, did I define it wrongly here? Sorry. Direction was wrong. This E after here is E dot. Yeah, here it will be B after E, which is defined as B dot E, and that is equal to B, again because E is identity. So those axioms are satisfied. What else is there? Associativity. Yeah, this is not a problem because you only have one object, so you don't have to check that. Anyway, normally you don't have to check that. Okay. This is satisfied. And that's it. So yes, this is a category. What if you take a monoid instead of a group? Does anything here fail? If you take a semi-group, identity may not exist. If you take a monoid, everything holds. So this is a special case of monoid as a category. So every monoid forms a single object category. Can we see the converse? What is a single object category? Suppose I have a category with a single object. So that means I have some category with some object. Then I have identity morphisms there. And then there are morphisms. Any two I can compose because domain is equal to codomain. Composition is associative. So ultimately, what is it? If I take a collection of morphisms, what does it become? It becomes a monoid. So monoid is exactly the same thing as a single object category. Okay. Monoid category in which every morphism is invertible is a group. Invertible will define the initial way, obviously. Okay, so we'll stop for now for lunch and we'll eat at 2 o'clock.